In this lesson, we're going to derive the law of sines, and it's pretty easy to derive. And the law of sines allows us to evaluate and solve a triangle that is not a right triangle. So here we have just a general triangle. He's not a right triangle. And our standard notation is we label the vertices with capital letters, and then we label the opposite sides with the lowercase version. So opposite of angle A is side A, and opposite of angle B is side B, and opposite angle C is side C. So here's what we're going to do. I'm going to draw in the altitude from vertex C, and I'm going to label that dimension H. Now in the end, I'm going to come up with an expression that doesn't have H in it, but this is a temporary measure. And let's see what we can do from here. So if I look at that, I now have a right triangle here. Angle A, and I have little h, and I have little b. So I can actually write an expression for the sine of A, because the sine of A is going to be h over b. So let me write that down. Sine of A is equal to h over b. And if you look, if you look at your diagram, I can write a similar expression for sine of b, because sine of b is going to be h over a. So sine of b is equal to h over a. Now I'm going to solve both of those expressions for h. To get h by itself, for the first guy, I'm going to multiply both sides by b. So these b's would reduce, and then I would have an expression for h. h is equal to b times the sine of a. And then I can do the same thing for the second expression. H is going to be equal to a times the sine of b. So I just took this guy and I simplified him there and solved for h. So I have two expressions that are in terms of h. Well, when two things are equal to the same thing, they are equal to each other. So I can set b sine of a equal to a sine of b. So I'll do that here. B sine of a is equal to a sine of b. And then all I have to do, depending on the version that you want to use, if I divide both sides by sine of a and then by sine of b, let's say I divide this by sine of a and this by sine of a, and then I also divide by sine of b, sine of b. What you're left with is a ratio that looks like the law of sines. Here's just a part of it. B over the sine of b is equal to a, side A, over the sine of angle A. Now this is all arbitrary. I could do this again. I could create an altitude from A and drop it and come up with an expression for side C. So all of this, basically, this is all of it is generic, and it doesn't matter which vertex I start from, but I can come up with the expression for the law of sines. So here's the meat. We're going to write down the official law of sines. If we want to put the sides in the numerator, we can say a over sine of a is equal to b over sine of b, and that's equal to c over sine of c. That is the law of sines, and that helps us find missing sides or missing angles dependent on what you are given. So we're going to take a look at that next. Just to have a diagram to go along with this law, again, as a reminder, it doesn't matter how I label these things, but this rule basically is dependent upon labeling the side opposite the angle. So that's the setup. So we can use law of sines when we have two angles and the included side in between. So let's say I have this. I'm given angle A and I'm given angle B, and I have a value for side C. Now right off the bat we couldn't use it, but what we can do is obtain angle C, because the measure of angle C is going to be 180 minus the measure of angle A and minus the measure of angle B. So we can always get angle C, and then we can use it to solve for whatever side we want to solve for. So angle side angle works for us. For a similar reason, angle angle side will work, because if I have the two angles and a non-included side, I can use that directly to find side B, or I can again find side angle C by subtracting, and I can always use it to find angle side. So if you think back to your triangle congruences, angle side angle is a triangle congruence. That means I can create only one triangle if I'm given two angles in the included side. The same thing with angle angle side. That was another one of our triangle congruences, where if I'm given the two angles and a non-included side, there's still only one triangle I can create. But there is a case where that's not true, and we call that the ambiguous case, and that's when you have angle side side. We can't just make one triangle with that. So I'm going to talk a little bit about the ambiguous case, and then we're going to practice all these in class. So here's what I mean when I say the ambiguous case, and I have a really good Geometry Sketchpad demo to show you in class 2 to kind of explain it a little bit better. Let's say I have a side, and this side length is not locked in. That side length can be whatever we want, but we have an angle measurement that's locked in. So this angle measurement's locked in, and we'll call this angle A. This side length is locked in. We'll call that side B. And let's say this side length is locked in. We'll call that side A. What's not locked in is this angle. I think Mrs. May called this the angle with the dangle, maybe. And what happens is, if this angle isn't locked in and this side length isn't locked in, then I can't tell you right off the bat how many triangles I can create, because there are different cases. With this particular length, A could be over here, or for the same length, it could also be over here. So that's two possible triangles I could create depending on the length of side A. Or if A is long enough, there's really only one triangle I can create. If this is angle A that's locked in and side B, and this side is long enough, I can only create one triangle. But there's also a chance that I can't create any triangle, because if A is a short little thing and he doesn't reach, because again this is locked in and this is locked in, then I have no solutions. So the ambiguous case is really all about finding how many triangle solutions do I have when I'm given specific dimensions. So I'm going to walk through an example of that, and we'll list some steps, and I'll kind of show you. I think you'll remember last year of how to do this. I'll show you the process that we go through. So here's an example I'm going to walk through with you. Determine the number of solutions of triangle ABC if angle A is 72 degrees, side B is 22, and side A is 21. So we're going to try to sketch that out a little bit. Again, this is angle, side, side. So I can't tell you right off the bat how many solutions we have. So here's how we typically set this up. We do a little chart, and we chart our angles because it's all in the angle measurements. If I'm not interested in just solving the triangles, if I'm just trying to figure out the number of solutions, which is typically this type of problem, I'm only really interested in the angle measurements, because that will tell me how many triangles I have. So angle A is locked in. He's not going to change, which means if I possibly have two triangles, angle A is going to be 72 degrees for both of them. So now we need to find angle B. So that's our first step. Find the measure of angle B. And we use law of sines for that. So basically A over the sine of A is equal to B over the sine of B. Now if I were to cross multiply, I would have A sine of B is equal to B sine of A. So I have an expression for the sine of B. I like to solve things algebraically first before I start putting values in. You should really only use your calculator in the last step. So when I have this, I'm probably going to run out of room here. So I substitute in, and I know B is going to be the inverse sine. You make sure your calculator is in degree mode when we do these problems, if I give you in degrees. And it's going to be 22 times the sine of 72 all over 21. That ends up being about 85.1 degrees. Now, for this type of problem, I'm going to round to a tenth, and that'll be sufficient because I'm just trying to figure out how many solutions we have. Okay, so once I have B, now I need to find C. C is going to be the result of taking 180 and subtracting 72 and subtracting 85.1. C ends up being 22.9. So I know I have at least one triangle because I have three angles, all of them are positive, and so that works out. Well, now we need to find the second B. And the second B is found, well, there's a couple ways to find it. But basically, the second B can be found by adding together A and C. So if I add 72 and I add to 22.9, let's see what we get. Let me see what I have in here because I can't do this in my head. The second C, or the second B, ends up being 94.9. So that's okay so far. Now I need to find the last C. I'm going to call him C2. C2 is going to be 180 minus 72 minus 94.9. And if he turns up to be positive, then we're good. And it looks like, I'm just looking at my old notes here, he ends up being about 13.1. So what this tells me, since I have two sets of angles and none of them are negative and there aren't any errors when I make a calculation, that means there are two solutions. Okay, so we're going to finish this lesson by just writing down these steps again. And I walked through an example, but now I just want to kind of write down step by step what you need to do. Alright, so I'm going to walk you through the steps for the ambiguous case. And the first step you need to do is to use the law of sines to find the first B angle. So I wrote that down like this. Use the law of sines to find B1. That's the first B angle. And then the second thing you're going to do is find the first C angle. So to find the first C angle, you're just going to take, you're going to subtract A and B1 from 180 degrees to find C. Now, if everything is positive, if these two both generate a positive value, then you know you at least have one solution. It could be the case that you have no solutions, and what will happen then is you can't even get an answer for B1. So if your law of sines isn't working right off the bat, that means you have zero solutions. But in this case, if you have B1, and then if you have C1, you have at least one solution. Now what you're going to do is you're going to add A and C to get the second B. So the second B angle is equal to the sum of A and C. We could draw that out sometime and I can show you, but for now just take my word for it. It works. So if that one works, then we go ahead and the fourth step is to find the last C in the same process that you used to find the first C. So you take 180 and from 180 you subtract A and B2 and that's going to give you your second C. So if these end up being positive, then you have two solutions. So your possible answers are going to be no solutions where right off the bat you can't get this to work, or you get a first C that's negative, or one solution where these guys work but these guys don't, Or if everything works, then you have two solutions. So that's how we walk through the ambiguous case. And what we'll do in class is we'll work a lot more examples on just basic law of sines and more of this ambiguous case.